Hey there, stats enthusiasts. Welcome back to our AP Statistics series on Unit 7, Inference for Quantitative Data, Means. We are now on Notes 3, which is going to be going over finding sample size for a margin of error, dealing with confidence intervals for means. And then we're going to switch over to talking about a matched pairs design and how we do our matched pair procedures. I'm Goldie, and I'm going to be taking you through this lesson today, so go ahead and sit back, relax, and let's dive into the content. Let's start off this set of notes talking about finding a sample size for a set margin of error. So oftentimes this is something we want to do in order to save resources. If we know we want a set margin of error with a certain degree confidence, what sample size do we need to have? So as a reminder, our confidence interval is statistic plus or minus some margin of error. So our margin of error that we use for a one sample t interval for means is this right here, where it's t star times our standard error, s over square root of n. Now, in our unit 4 proportions, we would just be able to plug the values in we want for our margin of error, our t star, and our s, and solve for n. But we can't do that as easily with means. We can't solve for n like we have before because there's actually two issues going on with this margin of error. And the reason we just can't plug in values and solve for n. The first is, even though t star corresponds to a percent confidence, the confidence level we want for our margin of error, we can't find t star without knowing degrees of freedom. And that largely depends on sample size. And unfortunately, there's not an algebraic way to determine degrees of freedom when we don't know our sample size. So that's our first issue. And then our second issue is that we don't know S. S relies on sample data, so if we haven't conducted the study, we don't know what that sample data is. So these are our two issues we run into when we're trying to determine a sample size for a mean. So we have two fixes for this problem in order to be able to do that. The first one is to use Z star as an estimate for T star. That's going to be our going back to our critical value, Z star, that corresponds to our standard normal distribution. And then the other fix is just to use a reasonable value for sigma based on past studies. So our margin of error to determine a sample size for a confidence interval for a mean is going to be this. It's going to look the same as the margin of error for a one sample Z interval for means. So we do have to make some assumptions about that, but that is the best we can do in order to determine our sample size needed for a set margin of error. So we're going to go through an example of what this looks like. So medical researchers would like to do a large study on cholesterol level of children. So they want their estimate to be within 1 milliliter per deciliter of the true value at a 95% confidence level. And previous studies have shown that the cholesterol level in children of this age varies with a population standard deviation of 5 milligrams per deciliter. What is the minimum number of children that the researchers need in their sample to get the estimate that they want? So we're given all of this information in the problem. Let's write down what we have. First, we have a set margin of error. They want their margin of error to be within 1 milligram per deciliter. Okay, so 1. And that's what they're measuring this mean cholesterol level in. We see that pop up again also in the population standard deviation. Okay, so our 95% confidence interval, our confidence level, that corresponds to a Z star level of 1.96. Remember, we use inverse norm there with our tail area in order to get our Z star. And then our population standard deviation of 5. Okay, so those are our three values, and we're going to plug them into our formula. Okay, our formula was, we had it written above there, but if you want to write it down in the problem again, and then I have those values put into the formula so that we can solve for n. Okay, so now it's just an algebra problem. We divide both sides by 1.96, and then we take 5 divided by 0.5102 and get 9.8. We square both sides and we get n equals 96.04. Now, we can't have 96.04 children. We need a whole number. And remember, we always round up for these. If we were to round down, we would lower the value of n. Lowering the denominator increases the standard error, and that's going to increase our margin of error, which we don't want to do. We don't want to go over 1 milligram a deciliter here. So we always have to round up. Okay, so they should use 97 children in this study on mean cholesterol levels. The second part of our notes here is going to talk about matched pair procedures. So we know that comparative studies are just more convincing than just single sample investigations. They're just more popular, they're more convincing, and we just do them more often. So for that reason, we have comparative inference, which is going to be a lot more common. Now, one of the ways we do comparative inference is with study designs making 2 observations on the same individual or 1 on each of 2 similar individuals. But these designs result in paired data. Okay? And when it results in paired data, we can run a matched pair procedure. And what you're going to see is that a matched pair procedure is almost identical to a significance test for a mean. Okay, and that's why we're talking about it right now before we get into our 2 populations in the next couple of notes. We're getting into it now because when we go through our example at the end of these notes, you are going to see that the procedure that we use is almost identical to the one we did in the notes right before this. But we need to recall a few things about this design. A matched pair procedure uses a matched pair design, and it's just a special case of a randomized block design. So using some sort of blocking variable, subjects are arranged into pairs and matched on relevant factors, whatever they may be. So in a matched pair design, there's really two different types of setups you could have. You could have 2 subjects into pairs, like I'm describing here, or you could have 1 subject receive 2 treatments. Okay, so those are the 2 classic setups that you see. Matched pairs, they may form naturally or they may be set up by the experimenter. But each pair receives both treatments. Okay, so again, if you have 2 subjects that are going to receive the treatments, one treatment to one member of the pair and the other treatment to the second member of the pair, if you're doing that design, the pairing has to be formed, like I said, either naturally or by the experimenter, but made sense in some way so that that pair are almost identical to each other, so that when you record any differences, you can assume that those differences are being done by the treatment and not by the differences in the subjects. So that's one way of doing it. Alternatively, you may get 1 subject that gets both treatments, and the order that the subject gets is randomly assigned. Okay, so again, 2 different types of pair designs. You can have 2 subjects and each of them gets the treatment and the order is just randomly assigned, or you have 1 subject and the 1 subject gets both treatments, and again, the order of that treatment is randomly assigned. And the idea is that either you pair them up so that the only difference between these 2 ends up being the treatment, or you just use 1 subject as basically their own control, so that if you use 1 person, any difference that you observe, because it's done on the same person, any difference would be attributed to that treatment. Okay. So you measure the same quantitative variable twice, one with 1 treatment and the other with the other treatment on the same subject or the same pair of subjects. You find the difference between the 2 data points and then you analyze the differences. Okay. So you're going to get two sets of data, the same quantitative variable twice, but then you analyze the differences between each subject. And you will use a one sample t procedure and perform inference on that mean difference. Okay, so this is why we're talking about it right now, and it's getting brought up right after our significance test for means, is because we're using the same procedure. We're just using it on a different type of study, a comparative study. These methods that we're going to do, they are called matched pair procedures. So here's the setup. Here's our 4 steps, very similar to what we've done. Not much is going to change, okay? The communicate, we're still going to communicate our hypotheses, our parameter, and our significance level. Our null hypotheses is that the mean difference is equal to 0, that there is no difference, right? Usually we're looking to see if there is no difference. It can technically be a value, but you'll mostly see your null hypotheses equal to 0 for this. And then our alternative can be greater than, less than, or not equal to. We do want to define what our mean difference is in words, and then of course communicate our significance level. Our conditions, we want to check for random assignment here. We want to make sure that those treatments are randomly assigned and the order that they are given is randomly assigned. We don't check the 10% condition because we are performing an experiment, so no need to check that. And then our nearly normal condition, we want to, if it's less than 30, if our sample size is less than 30, we want to graph to check for no outliers or strong skewness. Okay, if your sample size happens to be greater than 30, then the CLT says the sampling distribution will be approximately normal and there's no need to graph. Our calculate, it's the same test statistic where we have our t equals, we have our sample mean, our sample difference minus our hypothesized difference, which again is usually 0, divided by our standard error. And we find our p-value by using our t-CDF. And then our conclude is going to be the same conclusion as always, the same conclusion script. Because our p-value of whatever is lower, higher than alpha equals our significance level, we either reject or fail to reject the null. And then we do that in context from there. So here is our example. Okay, so I have all of the information here on one slide, and then we're going to go through and we're going to do the 4-step process for this example. So again, this is an experiment where researchers want to determine if a new type of medication will help lower glucose production on individuals with type 2 diabetes. So because there's a lot of things that go into people's lives who have type 2 diabetes, such as eating, exercise, weight loss journey, etc., they decide to do a matched pair experiment in order to control for all of those things that vary. So for 1 week, individuals will be placed on the new medicine and told to continue with their normal treatment of type 2 diabetes, and their blood sugar will then be recorded. And then for the next week, they'll be placed on their current medication for glucose control. And again, continue with your normal treatment and their blood sugar will be recorded. The experiment will be double blind, and the order the subjects receive the medication will be randomized. The following is a table of their results along with the difference between current minus new. So the way the table is organized, you see the current medicine first and then the new medicine on the next row, but they tell us in the description that the order that they received them was randomized. So we don't know if they got it for the first week or the second week, that order was randomized, but just to organize everything, current medicine, first row, new medicine, second row, and then the difference is in this third row here. Okay. Now, the thing with matched pairs and the way we determine that this is a matched pair procedure is, do these two values make sense to pair up? And in this case, they do. Okay. This is a single subject who received both treatments. Okay. Single subject did both treatments. So whatever their their eating, exercise habits were, it remained the same throughout each of the medicines. So that difference that we see of 0.2, we can then attribute to the difference of the medicines. Okay? And we see we have all of these differences here, and these are the data that we are going to be interested in. Do the data suggest that there is a significant significant difference between the current medicine and the new medicine for lowering blood sugar in people with type 2 diabetes. Use a 5% significance level. So it's very important here because some students will read this, is there a significant difference between the current medicine and new medicine? And they'll immediately think, oh, I'm going to run a 2-sample t-test, which we're going to talk about in the next couple sets of notes. But you're not running a 2-sample test because it's a matched pair procedure. So you're going to be very careful in having to identify this when you're given 2 sets of data. Am I interested in the difference? Or does it not make sense to pair these subjects up? And in this case, because it makes sense to pair them, it is a matched pair procedure. And so we're going to go through what that looks like. Let's define our parameter. Our parameter of interest is that mean difference in blood sugar levels between current medicine and the new medicine. And then I just define that the difference is current minus new. Okay? Current minus new. Now, when we set up our hypotheses, we want to answer the question, did the new medicine lower our blood sugar percentage? So when we're talking about the new medicine being lower, okay, if we're trying to find evidence for the new medication blood sugar levels being lowered, that means we're looking to find evidence of a positive difference. Okay, so our null is going to be equal to 0, and our alternative is looking for that positive difference. Again, because we set it up current minus new. So we want to see, is the blood sugar lower on the new? Okay, that's why we're setting this up with our alternative hypotheses being greater than 0. Now we're going to check our conditions. Our treatments were randomly assigned. They told us that in the problem, and we're good to go on our random condition. We don't have to check independence here because we did not randomly sample from our population. Okay, so remember, do not check 10% condition. In fact, if you check your 10% condition here when you did not randomly sample from the population, you will get points taken off. So don't do that. But we do have to check our nearly normal condition. Our sample size is less than 30, so we will check the data. Now, very important here, we're going to check the data on the differences. I say mean difference, but we're going to check the data on the differences. Okay. We do not care about the current medicine or the new medicine data. We don't care about the distribution of either of those because we are looking at the differences and the mean difference. That's what we are going to graph. Because I have to find those values anyway, I put them all in my calculator, and I'm going to let the calculator do the graph for me. So if I just go to stat plot, this is what comes up. So your first instinct is, oh my gosh, there's a visual outlier, right? And we talked about how if something appears that shouldn't, like strong skewness or an outlier, we want to comment on it. So I might need to comment on that, but I do want to adjust the screen because I see my min and my max here. My intervals aren't very great for copying down the graph. So I'm actually going to go to my window, and I'm going to change my y-scale to just be a whole 0.2. Okay, because I think by default it set it up as like 0.18, and I just want to make it 0.2 so that it's going to be easy for me to write down the graph. But once I do that, I see that my visual outlier kind of went away, okay, which might happen. If it was still there, I would want to comment on it, but the graph I'm going to copy down doesn't have any outliers or strong skewness, okay? So you're going to make it so that this is negative 0.2, this is 0, this is positive 0.2, positive 0.4, so on and so forth, and you're going to write down that sketch, okay? This is what you get, okay? Frequency and the differences, and then you comment, again, no outliers or strong skewness, so you're safe to proceed with those T procedures. Next, we're going to name the test. We're going to be in the calculate section here. We're going to run a 1-sample t-test for our means. I already have all of the data in our calculator, so I'm going to do my 1-bar stats, and I'm going to get the mean difference. I'm going to get the standard deviation of those differences, and then, of course, I have my n value there. Okay, so copy those values down from your calculator, and also at some point report the degrees of freedom, because you're going to need that to find your p-value. then we're going to put these values into our t-test statistic formula. So our mean difference is going to go right here. Mu sub naught, that was going to be 0. That comes from my null hypotheses. And I plug all of those values in, and I'm going to get a t statistic of 2.373. Okay. And then from there, I want to find my p-value. Okay. So this is going to be a job for TCDF. My lower boundary, upper boundary is positive infinity, and then my degrees of freedom are going to be 15. I put those in, and I get a p-value of 0.0157. Okay. Now I'm ready to go ahead and conclude here. And because our p-value of 0.0157 is lower than our significance level, we can reject the null hypotheses. And in the context of the problem, we have convincing evidence that there is a difference in the average blood sugar levels between the current medicine and the new medicine. Okay. So this matched pair T procedures, to summarize, they use a one sample T test inference procedure. Okay. It is a one sample T test for means, even though it's a matched pair procedure, and even though it looks like you have two samples of data. Okay. So this is going to be important to keep in mind as we go into the next couple sets of notes where we have two sample confidence intervals and two sample tests. Matched pairs is going to be handled differently than those ones are. And that wraps up today's lesson on Notes 3, where we talk about margin of error as well as our matched pair procedures. Thank you so much for following along. If you're ready for the next video, it's going to be Notes 4, which is going to talk about the confidence intervals for a difference in means. So go ahead and move on to that next video when you are ready. As always, if you have liked this video, please click the like button and subscribe to my YouTube channel for more great AP statistics content. I wish you endless statistical success, and I will see you in the next video.